Hello everyone, welcome on this e-learning platform of X Institute of Physics. Here is the general information about the instructor and the course. Electrostatics, the chapter we are talking about. Charge distribution is the topic we are covering. So that's the third video in charge distribution. Here in this video we will talk about volumetric or three-dimensional charge distribution. So let's proceed. Volumetric or volume, which is also called space charge distribution. So this is three-dimensional charge distribution. We can call it a 3D charge distribution as well. This says the charge is distributed uniformly over the volume of three-dimensional body. So that's called uniformly charged distribution or volumetric charge distribution. The density is defined by rho. So rho is equal to total charge upon total volume. If the total charge is denoted by Q and total volume is V, so Q by V becomes our answer in case of uniformly charged bodies. Now in case charge distribution is non-uniform, or in general we defined as dq upon dv, rho. So that's a rho. From here we can calculate the differential charge on differential volume as rho dv. So that's a differential equation, and that has to be used to calculate the differential charge on any three-dimensional body. Now we can further go for integration to calculate the total charge. Total charge Q on a body can be calculated after integration dq, which is going to be integration of rho dv. dv is a differential volume. Now if we use this volume dv, so this will require three-dimensional integration, but in our level this has to be reduced in a one-dimensional integration. So this dv will be written as 4 pi r square dr, and that will be for all those cases in which the charge distribution is radially symmetric. That means only radial direction varies the charge. So dv can be written as 4 pi r square dr, where we can put it here and can go for the integration and put the density variation, and this is how we can calculate the total charge on any volume or three-dimensional body. Let's take an example for that purpose. Let's take an example. So there is a sphere having a radius capital R, and the charge density is rho, and it is uniformly charged. So we can calculate total charge on this body, a spherical body. So total charge is going to be integration rho dv. Now we can go ahead, since it's a uniform, rho is going to be constant, rho can be taken outside, is integration of dv. We know integration of dv will lead to the total volume. Hence the total charge on this spherical object is going to be Q is equal to density into volume, and the volume of a sphere is 4 by 3 pi r cube. So that's the answer for total charge on a spherical body. Well, there's another example in which a spherical body, again we have a sphere, and that is of radius r, very similar to the earlier case, having a charge density rho, but this time let's say rho is non-uniform, so it's rho naught into r, and we need to find what the total charge is going to be. So if we are going to calculate the total charge, we will follow the same formula, rho dv, and then rho can be written as rho naught into r dv. As we have talked earlier, dv is going to be 4 pi r square dr, and if we see this integration we can perform, it's running from 0 to capital R. We can take the constants outside, which is 4 pi rho naught. Inside the integration we will find it's going to be r cube and dr. We know the integration of this quantity 0 to capital R. If we carry out, so total charge Q will turn up as 4 pi rho naught into this integration will lead to r power 4 by 4. Hence the answer will become Q is equal to pi rho naught r raised to power 4. So that will be the total charge in the non-uniform sphere. So this is how we can use it. Thank